This next item still on the determination of the number of prime numbers in specific range, in this case, which do not exceed 120. Now, some of the process here will just be duplicate of the previous process in the previous video, where we had actually 1 until 48 inclusive. So it's even smaller than this. Now we are trying to providing a large number so that we can actually look into its price as well. So before looking into this, I urge you to also review the previous video, as it will help you and guide you in understanding this next video here. So let's start with the idea of coming up with a certain set, right? So we have here, let S be the set of integers from 1, 2, 3 until 120. 120 is included because it will not exceed 120 in this manner. In short, our n is actually 120 as well. Now, in looking for this, we're going to use here the GPIE, okay, specifically the E of 0 perspective. Now take note, again, try to review the previous video. If we have here E of m, we're going to use here the omega of m minus m plus 1 taken m, omega of m plus 1 plus m plus 2 combination m times omega of m plus 2 until you reach minus dot plus negative 1 q to minus m. You have here q taken m, and you will have here omega of your q. Now, in simpler sense, there are actually a sum and difference. That's why we're using here inclusion and exclusion. The sum and difference of all the counts for each of the situation. First, if we have omega of 1, meaning we're going to take the summation of all omega containing p of 1 characteristic. So the number of elements that satisfy or that possess one specific characteristic, we're going to count that per set, and we're going to combine them to form omega of 1. Omega of 2 will also be the summation of the omegas of the combination, let's say p sub I sub 1 and p sub I sub 2 pairs of characteristics, combine them, so on and so forth. That's also true for omega of 3 and omega of 4. We're going to talk about that later as well. And of course, the idea that all of this could be easily solved, this formula is even easier if we're going to look at it differently. Because this talks about the number of elements, what do you call this one? The number of elements in the set S that satisfy the properties. But if we're going to look at it an opposite way, we are going to invoke the use of E of 0. E of 0 is actually the idea of finding the number of elements having none of the properties. Let's try to describe the properties as divisibility so that it could target composite functions, the opposite of the prime, so that E of O will be applicable. Let us say, how do we identify the properties? Now, take note, our n is 120. We can actually identify the number or the prime numbers that are prime divisors of this, taking into account the square root of n means square root of 120. This is equal to approximately, or you have here 10.95, so on and so forth. So the prime numbers less than 10 are, we'll be using here 2, 3, 5, and then 7. So this would be our p sub the p properties. So for our p sub 1, let us say it talks about all numbers divisible by 2, p sub 2, all numbers divisible by 3, p sub 3, all numbers divisible by 5, and p sub 4, all numbers divisible by 7. If we're going to consider all of these properties and combine it later on with our process, this tells us that we're going to count all the multiples of 2, 3, 5, and 7. And if we're talking about E of 0, having none of those, having not multiples or non-multiples of 2, 3, 5, and 7, then they are the prime numbers we're looking for. Let's start here. Now, we know that in general sense, the omega of 0 is actually just equal to the cardinality of S. That means 120, so that's already okay. Now, for the the omega of 1, actually, again, it is summation of all omega having one characteristic, okay, p sub I characteristics. So we're going to solve for each of the cardinality for each of the property. I'm talking about, say for example, if we talk about the omega of p sub 1, meaning we're talking about the number of elements that are divisible by 2, that's here. So we're going to use here the floor function of 120 divided by 2. That's exactly 60, right? Okay, that's 60. Next, for omega of p sub 2, that's for the divisibility by 3. That's 120 divided by 3. The floor function will still be exact, 40. Next, for omega of p sub 3, that's divisibility by 5. That's actually 120 divided by 5. That's exactly 24. Okay? But if we have here omega of p sub 4, which talks about divisibility by 7, this time the floor function will give us a value rounded off because 120 divided by 7 is not exact, but according to the floor function, 120 divided by 7, that's actually 17. That's the purpose of our floor function. All of this comprises the result here because omega of 1 talks about the summation of all omegas per property, or meaning the number of elements that satisfy or possess exactly one property. 60, 40, 24, 17, which gives us, again, 60 plus 40 plus 24 plus 17, you have 141. So you can see this is very large as compared to that because some needs to be removed. Hence, the topic on inclusion and exclusion. Let's proceed to omega of 2. By the way, where do we end up? We will end up actually at omega of 4 because there are 4 properties, and what if we combine all of them? So we will be using another page for this, so please bear with me. This will be the summation of all omegas of p sub I sub 1 and then p sub I sub 2, meaning all all elements that share or has exactly 2 properties. So for your omega of p sub 1 and p sub 2, this predicts the divisibility of 2 intersection 3. That's actually divisibility by 6. So according to the floor function, 120 divided by 6, you will get here 20. Okay, so that's the intersection for 2 and 3. For the omega of p sub 1, p sub 3 rather, that's actually what do you call this one? Divisibility by 2 intersection 5. That's divisibility of 10. So the floor function is still exact. 120 divided by 10, that's 12. Let me write here. So I'm going to use a lot of space. I'm going to use other page as well. P sub 1, P sub 4. Okay? 1 and 4, that's divisibility. Cardinality of divisibility of 2 and 7. That's actually the floor function of 120 divided by 14. So we'll get here a result of 120 divided by 14. So the floor function is actually equal to 8. Now let's move forward. We still have more. The omega of p sub 2 now and p sub 3 is actually for 3 intersection 5. And that's actually divisibility of 15. So the floor function of 120 divided by 15, if I may, 120 divided by 15 is exact to be 8. Next, the omega of p sub 2 and p sub 4. So that's actually d of 3 and divisibility by 7. So that's divisibility of 21. Floor function 120 and 21. 120 divided by 21 is actually 5. Then, I believe we still have one more for the divisibility of 5 and then divisibility of 7. That's actually 35. So that's 120 divided by 35. The floor function of that will give us a result of 3. So all of this, 6 of this, will comprise the omega of 2. So simply add them. 20 plus 12 plus 8 plus 8 plus 5 plus 3. So you have 20 plus 8 plus 8 plus 5 plus 3. You will get here, sorry, again, 20 plus 12 plus 8 plus 8 plus 5 plus 3. You will get here 56. So there are 56 elements in our set S with what do you call this one, having or possessing exactly two of those properties, whether or not it is divisible by 2, by 3, by 5, and by 7. Now let's move to another page. I'll be adding a page here for us to continue for the groups of 3 and even the 4. So we have here omega of 3. This is summation of all omegas of p sub 1 sub I sub 1, p of that's intersection, right? So p I sub 2 and p I sub 3. So we are to identify first their independent cardinalities of 4, p sub 1, p sub 2, and p sub 3. Actually, that's the intersection for the set for integers with divisible by 2, 3, and 5. That's actually divisibility by 30. So a floor function of 120 divided by 30, we will get here 4. There are 4 of them. Next, we will have here p sub 1, p sub 2, p sub 4. So that's d sub 2, d sub 3, d sub 7. So basically, that's 2 times 3 times 7. That's divisibility by 42. So you have floor function 120 divided by 42. You will have 2. Next, p sub 1, p sub 3, p sub 4. That's divisibility by 2, by 5, and by 7. So 2 times 5 times 7, that's actually by 70. So 120, of course, there's only 170 there. Okay? I believe we still have one more. 2, 3, 4. That's 3, 5, 7. 3 times 5 times 7 is 105. Of course, that's 120, 105. Again, we only have 1. So I believe these are all. Can we still get some? That's actually 4 combination 3, right? How many are they? So there are only 4. Okay, so 4, the omega of 3, the sum of all of this, 4 plus 2 plus 1 plus 1, we'll get here 8. Next would be the omega of 4, which is just equal to the omega of p sub 1, p sub 2, p sub 3, p sub 4, because this is actually, you have exactly 4 elements. This is actually the intersection of 2, 3, 5, 7. So that's actually the for divisibility of 200, so 210. But the floor function of 120 and 210, since there's no number that can be divided with that, so that's 0. So all of this, now proceed to our E of O. It's the W of O, or omega of O, sorry, minus omega of 1 plus omega of 2 minus omega of 3 plus omega of 4. This simply place here omega of 0 earlier. It was actually 120. So 120 minus omega of 1 is this one here. 100, sorry for that, 141 plus omega of 2 is somewhere here, 56. Sorry, that's 56. Minus omega of 3 is here, 8, exactly 8. And plus a 0 for this case. So this is our E of 0. 120 minus 141 plus 56 minus 8. You will have 27. What does this stand for? Since we talk about E of 0 having none of those properties, that would mean 27 elements in the set S containing 1 until 120 do not possess divisibility by 2, 3, 5, or 7 in their combination. Hence, these are the primes that are considered in that specific set S 1 to 120. But are these the only primes? Take note that we started with the idea of removing, right? We removed this one here. We removed that, our omega of 1 from omega of 0, being this 141 and 120, right? So we remove something. This includes the removal of the prime numbers we use 2, 3, 5, and 7, because they also possess the characteristic for each of their assigned assigned property or sets. So once they were removed, you would be able to see that they were also added here, and then they were also removed here. So to return to that, because 2, 3, 5, and 7 are also prime numbers that doesn't exceed 120, but they were removed, we need to add them. So it's actually the number of prime numbers. So that's prime numbers that do not exceed 120, that's actually E of O plus 4 of those. Again, because they were removed. They were removed in the process here. They were counted here. They were removed. They were counted again. They were removed. So they were removed, but we are looking for number prime numbers. We had that. Is this not a final answer? I still have one more thing to say. We need to subtract 1. What is that 1? In the process of this, we started from 1 to 120. All of them are counted here. But look at the very first element 1. Okay? This element was not removed in the process here, nor added at the same time. It just stayed there until the last portion. So here, in our E of 0, 1 is still included. But since the question talks about prime numbers and 1 is not prime, so we're going to remove that perspective. We remove that 1 1 in our total because 1 is not a prime number. Hopefully this is understood. This is the number of prime numbers having characteristics, exactly those having none of those properties or characteristics. They are not longer divisible by 2, 3, 5, and 7. Then we add 2, 3, 5, and 7 because they were removed, and then we remove 1 because the 1 is not prime. Hence the total here is 27 plus 4 minus 1. We will get 30 prime numbers less than 120, or I mean less than or equal to 120 because do not exceed 120. This is now the answer to this item. Yes, very long, but basically still using the generalized principle of inclusion and exclusion and all of our understanding of prime numbers, considering the topics before discussed, such as sieve of Eratosthenes and anything. By the way, you can verify this using sieve of Eratosthenes. You can do that on your own time. Thank you very much for watching.